Hi, this is Group 7. The process of engineering the design of a structure can be broken into 3 key steps: data analysis, ideation, and the CAD phase. The first step to deriving the response of a structure was to isolate relevant disturbance information from the available dataset, namely the accelerations in the north-south direction. After generating a frequency response on seismo signal, the displacement for the maximum period of 4 seconds was taken and scaled to 15 mm and 30 mm. This can allow us to accurately set up external forces on the structure when performing a SolidWorks simulation. In terms of ideation, we visualized our ideas with sketches and quickly came to the consensus that a hammered shape design would be the most effective and most interesting to explore as a potential final design. So upon making this decision, a rough prototype was made on SolidWorks, which was distinguished by a rounded pillar and base. Desk research was then carried out to implement accurate PLA material property data, which would accurately reflect the 3D printed fill for additive manufacturing. This increased the reliability of the natural estimations on SolidWorks. So after performing a simulation and obtaining the frequency response spectrum, the initial period was 0.039 seconds, which was found to be considerably smaller than the required specifications. However, this motivated us to optimize the structure and reconfigure for our final design. Upon multiple iterations, 3 main changes were made. Firstly, the pillar of the final structure was modified to 2 smaller quadrilateral pillars, better satisfying the demand that the motion should be unidirectional without any rotational motion, and this increases the natural period. Secondly, to minimize the structural mass, the top housing was removed with the 2 weights being stabilized exclusively via mechanical fastening. Thirdly, the base was changed to a cuboid, mirroring the shape of the top platform, and this was redesigned to be fixed to a shaking table with only 1 bolt. Using the most significant 4 seconds of the acceleration record from the Peru earthquake, the maximum predicted displacement is approximately 14.5 millimeters, which occurs 0.5 seconds into the 4-second periods and corresponds to the largest single acceleration of 6.5 centimeters per second squared at 63.5 seconds in the earthquake acceleration spectra. In terms of testing, the structure is fastened with 2 metal weights on the top with a bolt and nut. It is then fixed to a servo mechanically actuated unidirectional shaking table, also using bolts and nuts. For the shaking test, the acceleration record of the northern Peru earthquake is used, scaled to a peak ground displacement value of 50 mm and 30 mm. Firstly, the most significant 8 seconds of the displacement was extracted from my experiment video. This corresponds to a period between approximately 62 and 70 seconds of the actual Peru earthquake data. After importing this 8-second footage onto Tracker, the motion of the bullseye target attached to the camera-facing side of the mast, which was itself attached to the structure, was tracked frame by frame across the 8-second interval, with the calibrated system calculating the displacement from the start position at that frame. These results were then analyzed in conjunction with the simulations we've previously performed on SolidWorks, as well as the actual earthquake data we've plotted on seismo signal. The maximum absolute displacement of the structure is very high, reaching a maximum of 50 mm, more than 3 times the estimated 14 mm. The first possible cause for the difference is that the actual mass of the structure is significantly larger than what was considered for the simulation, which was 4 grams based on its dimensions, fill percentage, and printing material. However, measuring the final printed structure, it actually weighs 16 grams, an increase of more than 400%, which could explain the drastic increase of the displacement between the estimation and real test results. This is because the greater mass causes a larger force to be exerted on the structure for the same acceleration. Secondly, it can also be observed that the real displacement oscillates far more than in the simulated response. Therefore, the period at which the maximum displacement occurs is also largely different to the simulated waveform. Considering that the results of the most significant displacement are not the largest acceleration nor velocity peaks present in the earthquake spectra, this is rather peculiar. Nonetheless, given that the initial peak displacement is not significantly different from the predicted peak, and that the real displacement continues to increase long after this, reaching its true peak much later, this indicates that the effective of constructive interference in the forces affecting the structure were not sufficiently accounted by the SolidWorks simulation. So with a mass of 16 grams and a natural period, we learned that elastic structures accumulate kinetic energy leading to higher magnitudes of oscillation than we would have predicted. So instead of modeling a static structure, the structure should have been modeled as a spring, and the peak displacement should have been calculated by accumulating the energy provided by the earthquake with some realistic factor of decay. Once absorbed energy is known, we can obtain the displacement using Hooke's law. Overall, working with multiple design constraints simultaneously was not an easy task, as we had to ensure that the dimensions and the requirements for the final achieved natural frequency were simultaneously satisfied. However, this also gave us the opportunity to learn and harness the power of CAD as a tool for designing, manufacturing, testing, and analyzing a small-scale structure and its shaking characteristics. So if we were to improve on the structure, we would use the empirical solutions to iteratively refine our design to be more robust. This would enable us to make more accurate estimations and converge at a more refined solutions with a small error relative to the specified parameters. That said, we're still happy to see our part survive the emulated earthquake. And with that in mind, thank you so much for watching.